So, good afternoon, everyone. We will continue with the next lecture, which is lecture 5 in this series in the electricity and magnetism. Now, we have finished up with some of the basic concepts in magnetic field. Now you understand what do you mean by magnetic force and how it actually affects in different examples. The way to explain much of it is actually Biot-Savart law, and we already know how to apply that with straight wires, circular loops, and different current loops, dipoles and dipole moments, and how these things are calculated. Ampere circuit law is rather a simpler way of getting magnetic field. The expressions of the magnetic field for numerical solutions and other things are quite useful. The properties of magnetic field, which is B, the curls and the divergence, vector potential, and most of it, for some examples, have been discussed already. Now, we have also discussed about magnetic properties in different matters. I mean, like how magnetization changes and magnetic intensity changes for depending on the material, susceptibility, permeability, and all that are already been explained. pH curve and all this hypothesis hysteresis is like supposed to be already within your understanding. Now we have a good background to get into electromagnetic induction. So in electromagnetic induction, what is expected is we will have understanding about Faraday's law, Lenge's law, the self-inductance and mutual inductance and all that. I'll discuss it in a different class. The reciprocity theorem and other things. Then we'll move into the energy stored in the magnetic field. Then we'll get into more into electromagnetic waves, and one of the core theory is Maxwell's equation, get into the charge conservation and displacement of current with that. Then we'll further go into various other concepts. Now, much of it can be well read from the Griffiths book of electrodynamics, but definitely there are other books which you can follow. Now, to give you an introduction of electromagnetic induction, basically any changing magnetic field, the change can be in terms of intensity or even movement, any kind of movement will induce an electromagnetic force. Now, it's same as in a closed electric field, electric circuit. A changing magnetic field will produce electric current. That is basically the simpler version of the Faraday's law, which says the induced EMF in a circuit is proportional to the rate of change of magnetic flux through any surface bounded by the circuit. We'll discuss in detail, but basically you need to know what is EMF. In electromagnetic induction, EMF can be defined around a closed loop of conductor as the electromagnetic work that would be done on an electric charge, an electron for this example, if it travels once around the loop. So Faraday did several experiments to reach to these conclusions. And he discovered that way back in 1831, which is basically the foundation of most of the electrical devices which are around us. from your fan to the motors that propel most of the devices around us. So he figured that moving the magnet induces a current. Reversing the direction reverses the current. Moving the loop induces a current. And the induced current is set up by an induced EMF. So all this he figured from an experimental analysis, which is he used a closed coil near a magnet. And by moving it near and away from the magnet, he realized that there is a current. So you must have some kind of a measurement device to see the current actually changing. It could be a galvanometer. While you reverse the direction of this movement, this will actually reverse the current as well. So something is happening because of the movement of the magnetic field. While you move the loop, what I mentioned is that closed electric circuit, it induces a current. The induces current is set up by an induced EMF. We'll discuss more in detail. If you set up two of these loops close to each other, like Faraday's experiment did, he figured that changing the current in the right hand coil induces a current in the left hand coil. The induced current does not depend on the size of the current in the right hand coil. So whether you have a bigger size of the coil or a smaller one, the induced current will not depend on that. The induced current depends on di by dt, which is the change of the current with time. The concept of magnetic flux was partially introduced. I think it was quite well introduced in your earlier chapters when we calculated magnetic field for various objects. And now we know that in easiest of the cases, the constant magnetic field, which is B, at a flat surface, the magnetic flux will be simply the multiplication of this area with the magnetic field. And this has a unit of Weber. But in case you have a complicated system and B is not constant or the surface is not flat, then you have to do an integral. Now, in terms of Faraday's law, mathematically, it can be explained in this way. So in case of Faraday's law, while moving the magnet changes the flux in one of the coil, and that can be called a psi B. The changing the current changes the flux also. So whether you're moving the magnet or you're changing the current, in both cases, the magnetic flux will change. So Faraday concluded that changing the flux induces an EMF. So the EMF which is created here is because of the change of flux, because the flux is actually changing with the movement of the magnet or the movement or the change of current. So either of these two is actually triggering a change in flux. And the change of flux is actually introducing an EMF. Now the change of the flux is happening in terms of time. So Faraday's law can be explained In simple, the EMF induced around a loop is equal to the rate of change of flux through that loop. Lenge's law is another interesting law. While Faraday's law gives the direction of the induced EMF and therefore the direction of any induced current, Lenge's law gives the direction with less effort. In Lenge's law, it is mentioned the induced EMF is directed so that any induced current flow will oppose the change in magnetic field, which causes the induced EMF. It is easier to use than to say. So, when we have a scenario where decreasing magnetic field, the EMF creates additional magnetic field. While we are having a scenario where we have increasing magnetic field, increasing flux, the EMF creates opposite magnetic field. So in simple, Lenge's law is a law which predicts exactly how the direction of the field will happen. In simple, it will always try to oppose the change in magnetic flux. So in current scenario, if you think, if we move the magnet towards the loop, the flux P will increase. In simple, because you're going closer to the loop, then the diverging magnetic field will be higher, nearer to the magnet, and that is why the flux will increase. Now, Lorentz law mentions that the current induced in the loop will generate a field which is B star that will actually oppose this current. We can have a numerical example of Faraday's law. If you consider a radius 5 centimeter with 250 turns, a magnetic field B passing through it, and it has a time variant magnetic field with fixed resistance. The induced current, the direction of that can be very easily calculated with Lenge's law to determine the direction of the induced current. And Faraday's law can be used to calculate the EMF and then the current. Lenge's law, the change in B, which is the magnetic field, is increasing the upward flux through the coil. So the induced current will have a magnetic field whose flux and therefore field will be down. Hence, the induced current must be clockwise when looked at from the above. Now we use Faraday's law to calculate the EMF. From Faraday's law, we know the equation of EMF is this. So we first calculate the flux, and then we do the rate of change of the flux, which can be done by dB by dt. Motional EMF is another interesting concept. Up until now, we have considered fixed loops. The flux through them changed because the magnetic field changed with time. Now, if we consider a scenario where we are moving the loop in a uniform and constant magnetic field, this will also change the flux. This gives rise to an EMF, which is the motional EMF. It can be calculated very easily because the change of the flux can be B into A, which is B dx here. It changes with the time depending on the velocity. And so in Faraday's law, there is an induced EMF and current. Now, how do you calculate the direction? With Lenge's law. There is less inwards flux through the loop, hence the induced current gives inward flux. So the induced current is clockwise. From Faraday's law, we can calculate this motional EMF as B V. As we know, the EMF is equal to I into R. From this, you can actually calculate the current induced through this. Thus, the moving a circuit in a magnetic field produces an EMF exactly like a battery. And this is the concept and the basis of creating all these electric generators that we use today. The change of flux, which induces this current, is actually created with a rotating loop in case of electric generators. If we consider a loop of area A in a region of space in which there is a uniform magnetic field B, and we continuously rotate it with the angular frequency omega, the flux changes because of angle theta, and that changes with the time omega t. Then from Faraday's law, we find so the EMF will be BA omega sine omega t. From sine omega t term, we can see this is an alternating generator. It's the current that will be produced by this will be alternating current. If we have a conducting loop in a magnetic field, we can create an EMF like a battery by changing the value of P dot A, which is the flux. This can be done by changing the area, changing the magnetic field or angle between them. We can use this source of EMF in electrical circuit in the same way we used batteries. We have to do work to move the loop or to change the P to generate the EMF. And that is where the conservation of energy is actually restored. Induced electric field is also a concept we have to understand from this. Consider a stationary conductor in a time-varying magnetic field. Current starts to flow. So the electrons must feel a force, which is F. Now this force is equal to Q into E due to the induced electric field. It will not be Q V cross B, which is in case of a magnetic field, because the charges started stationary. So in this case, a time-varying magnetic field causes an electric field to appear. The E along a path gives a voltage difference, which is E dot dl, integral over the path. So the motion of the EMF, as we know from Faraday's law, can be actually from this closed loop can be can be just drawn like E dot dl in the closed loop. So that changes the Faraday's law as we have written before. And Faraday's law becomes E dot dl in a closed loop equals to the change of magnetic flux, rate of change of magnetic flux, which is minus d sine by dt. The electrostatic field E is conservative. So clearly this one will be zero in a closed loop. Consequently, we can write it as a gradient of V. The induced electric field E is not a conservative. So this is definitely different. And we cannot write it in terms of a scalar voltage. So in case of an electrostatic field and induced electric field, you can already see it's not exactly the same thing. Because the electrostatic field is conservative, while the induced electric field is not conservative. Work or energy difference does not depend on path for electrostatic field, while the work or energy difference does depend on path for induced electric field. This is because the induced electric field is caused by changing magnetic field. You cannot just create it with a stationary charge or EMF sources like electrostatic field generally. Go in further detail of the induced electric field. From Faraday's law, now we understand if we suppose there is no conductor, will there be an electric field? There will still be some electric field. The field does not depend on the presence of any conductor. For a magnetic field with axial and cylindrical symmetry, the field lines of E are circular. These concepts are heavily used in case of transformers. In transformers, you have two coils side by side. A primary coil connected to a voltage source and a secondary coil, a galvanometer. When the voltage source is turned on, the current briefly surges to the secondary coil. When the voltage source is turned off, the current briefly surges to the secondary coil in the opposite direction. The magnetic field building around the primary extends to the secondary. Changes in magnetic field intensity induce voltage in the secondary. Placing a core within the coils will intensify the magnetic field. This we know from our concepts of magnetic fields in materials. The secondary will intercept more of the field that will change. Instead of switching a DC voltage source off and on, the device is connected to an AC voltage source. The rate at which the magnetic field changes is equal to the frequency of the AC current. This device is known as transformer. Transformer is used to step up voltages or step down. These are used in AC adapters. When the voltage is stepped up, the number of the coils turns in the secondary greater than the number of turns in the primary. Voltage is stepped down when the number of the coils turns in the secondary is less than the number of turns in the primary. Since voltage can be stepped down or up so easily, electrical power is primarily in the form of AC. Now, induction of electric and magnetic field in simple. One of the basic concepts it follows is Faraday's law. Electric fields are created in any region of space where a magnetic field is changing with time. Well, in terms of Maxwell, the concept we'll introduce next. A magnetic field is created in any region of space where the electric field is changing with time. These laws are inverses of each other and lead to the concept of electromagnetic wave.